Welcome back to our lessons, everyone. Mrs. Hanson once again, picking up a conversation about Gibbs free energy, most often called free energy, and with abbreviation of G for Gibbs. The method used so far in determining whether a spontaneous reaction is occurring had us evaluate two quantities. Those would be both the delta S of the system, which is our reaction, as well as delta S of the surroundings. And we know that it is very inconvenient, very difficult to measure entropy changes of surroundings. So J. Willard Gibbs, working in the late 1800s, made the following assertion, saying that the maximum non-pressure volume work available to do work on a system, that's what Gibbs free energy is a measure of, is available work. Well, it's a function of both enthalpy and entropy. And that relationship has delta H, which we know as the enthalpy of reaction, the heat of reaction, T being the Kelvin temperature, and S being the entropy, the dispersal of energy, relate to the spontaneity of a reaction. So delta G, Gibbs free energy, is a relationship between the two thermodynamic properties of enthalpy, which is heat, and entropy, which is the disorganization of the system. And when we look at the impossibility of measuring specific values, it's more convenient to talk about changes in value. And so here's our equation. This is the one that you should know how to use and manipulate for those variables, that says at constant temperature, Gibbs free energy, which is just free energy of a system, is related to the enthalpy change minus the product of the Kelvin temperature and the standard state of entropy. The standard state conditions, right? That's 1 atmosphere of pressure, 25 degrees Celsius. So sometimes you'll see that as 1 bar and 298 Kelvin. Those are the standard state conditions. Gibbs free energy is a relationship that will tell us if a reaction is spontaneous by looking at the enthalpy value and the entropy value and the temperature with which the reaction occurs. So let's put this together. The sign of delta G is what's important to us. Think of the delta G as really as a measure of the driving force of a reaction. The sign will indicate if a reaction is spontaneous or not. Now, if delta G is negative, delta G is less than 0, the reaction is said to be spontaneous in the forward direction. So if I have a reaction A plus B yields C plus D, and the standard Gibbs free energy value comes out to be negative, let me just make up a number, negative 50 kJs per mole. That tells us that this reaction is spontaneous in the forward direction. It would be non-spontaneous in the reverse direction. If delta G is a positive number, the reaction is not spontaneous in that direction. So for instance, if I were to look at A plus B yielding C plus D, what if we reverse that reaction? Read it in the opposite way. Delta G, of course, which is a state function, would become a positive value, reading it in the reverse direction. So, of course, this would be spontaneous in the forward direction. This would be non-spontaneous if I read it with D plus C going back to A plus B. Negative values show us spontaneity. The negative sign on a delta G says that reaction is spontaneous in the direction as written. And if delta G is at 0, what that tells us is that we have an equilibrium, that we have a forward and a reverse reaction occurring at the same rate. And I know equilibrium is our topic for the next 3 chapters, but we'll also be sprinkling it into this lesson as well. A system that is in equilibrium has a forward and a reverse reaction occurring at the same time, and so delta G is 0. If the delta G is negative in the forward direction, it's spontaneous. And if it's negative in the forward direction, it'll be positive in the reverse direction. Now, what are some conditions on enthalpy, heat, and entropy that are favorable to create spontaneous reactions? Well, the most favorable condition for heat is to have a negative enthalpy. Negative enthalpy tells us that it's exothermic. A negative delta H contributes to a negative delta G, so that's favorable. Another favorable variable is an increase in the entropy. We want a positive entropy to contribute to a negative delta G. Now remember, that's because there's a negative sign here. The Kelvin temperature times a positive value of entropy is going to create a negative delta G, and that's a favorable indication of a spontaneous reaction. Now, that doesn't mean that those are the only ways that we can have a spontaneous reaction. Delta H could be endothermic and still have a spontaneity reaction. Or we could have a negative entropy and still have a spontaneous reaction. So both play a role. Entropy and enthalpy must be utilized together to determine if delta G will indeed be negative, spontaneous, positive, not spontaneous, or is it indeed zero? And notice that there is a temperature dependence as well. So raising the temperature could affect the spontaneity of the reaction. Now, I like this particular chart to help us think about 4 different scenarios and whether or not a reaction will occur. Now remember, enthalpy minus the product of T delta S. This overall must give us a negative delta G to be spontaneous. If, let's say, in reaction type 1, if delta H is negative, that means it's an exothermic process. That's a good thing. That's favorable, isn't it? Exothermic reactions. And if delta S is positive, it's becoming more disorganized. That tells me that no matter what temperature, delta G will always be a negative value, spontaneous, at any given temperature. What if we have an exothermic process, which we said was a favorable reaction, but the system is actually becoming more organized so that the entropy is unfavorable. It's a negative value. Now it's going to depend upon the temperature, isn't it? Because the temperature directly affects that entropy value. So we want to think about lowering the temperature, very low temperatures, to create a spontaneous or favorable Gibbs free energy. Now that tells me that if the system is becoming more organized, I don't want that to be a large factor in determining the sign on delta G. You want to minimize that, and that happens with low temperatures. Now in an endothermic process, delta H is positive. So if this guy becomes positive and we still want this to be negative, we need very, very high temperatures to have this factor dominate the sign of delta G. So favorable entropy and high temperatures are enough of a driving force to overcome endothermic reactions. The system must be gaining in chaos, gaining in disorganization to have enough of a power to overcome endothermic processes. And the last case says, if I have an endothermic reaction and the system is becoming more organized, there is not any temperature possible to drive that reaction in a spontaneous direction. So if both are unfavorable conditions, that reaction just will not occur in the direction written. Here's another snapshot of those same 4 scenarios. Up on the top, we talked about enthalpy. If enthalpy is endothermic, we know that delta H is positive. And if enthalpy is exothermic, we know that delta H is negative. Of course, this is the favorable condition. And so delta G at any temperature will be a negative sign for spontaneous as long as the entropy is gaining, and that becomes a positive number. We said here, if delta S is negative, that means it's becoming more organized, and I have an endothermic reaction. This will never be a spontaneous condition. And it's this system here that if I have exothermic, I want low conditions if the reaction is gaining in order. And then over here you want delta H to have high temperatures so that the entropy will dominate the endothermic reaction. You really should take some time and thoroughly study these 4 different scenarios so that you're ready to apply questions and answers about conditions of spontaneity. What has to happen to the temperature in order to drive the Gibbs free energy to be a negative, indicating a spontaneous reaction? And let's do some practice with these. Here's a sample problem, and it looks like a busy slide, so let's kind of take it one step at a time. Let me put we'll shield this and kind of go through it one step at a time. Let's calculate the standard entropy of reaction for the following using the data in this table. Now remember, I said that this is a thermodynamic table that's provided in your text. You just click on it and the appendix comes up. And remember that the first one here is delta H, here's delta G, and this last one would be delta S, just so that we remember the order of that chart. When we want to know the delta S for the reaction, do you remember that formula? The delta S of the reaction is equal to the sum of the delta S of the products minus reactants. And so this begins really with just an idea of going back to review from last lesson, how to calculate the delta S of a reaction. The C6H6 as a liquid has a delta S of 173.4, and remember that unit is a joule per Kelvin mole, and that acetylene C2H2 in the gaseous form has a delta S value of 200.9, and again that's a joule per Kelvin mole. So the delta S of the system, or the reaction, those are identical words, is going to be equal to the sum of the products. We have just 1 mole of the C6H6, so that's 173.4 minus the sum of the reactant. Well, we have 3 moles worth of acetylene, so 3 times the value of 200.9. Whoops, that's a joule per Kelvin mole. And hit that with me on your calculator, and let's see if we get a common answer. Pause the video if you need to. Make sure you can process and find the same answer as I do. 173.4 minus 3 times 200.9, and my screen reads negative 429.3. Now pause a minute and just make sense of this number. We have 3 gaseous moles converting to 1 liquid mole. Certainly that is becoming a more ordered state, so that makes sense to have entropy as a negative sign. It's becoming more organized. Now let's calculate the standard Gibbs free energy of the reaction. And in order to do that, the Gibbs free energy, remember our formula? We just wrote it out. The delta G for this reaction is equal to the delta H, and these are standard state conditions, minus the product of T delta S. Now, let's emphasize something we've been doing all along, but let's say it again. I know that delta G is in a kJ per mole. I know that delta H is in a kJ per mole. And I know that entropy is in a joule per mole Kelvin. I want to emphasize that when we place these variables into the same equation, we need to make sure they're all in the same unit. We have to subtract like units. So I'm going to convert my entropy value into kilojoules since I'm required to report my Gibbs free energy in a kJ anyway. So recall that there are 1,000 joules in a kilojoule. Let me write that better. There's 1 kJ set over 1,000 joules. You're sliding your decimal 3 points to the left, so that becomes negative 0.4293. And now that's a kJ per mole Kelvin. I'm going to solve for delta G of this reaction by placing the delta H. Notice how that was given to us up here? It was already provided for us. Even though I could have found it from my thermodynamic value by taking the sum of the products minus reactants using the delta H value, I could have found it from this chart. But what was so nice about this particular homework problem is they solved for that already. So the delta H is given to me as this value, negative 633.1, and that's in a kJ per mole. That's our delta H value. And I'm going to subtract the Kelvin temperature, which is 25 Celsius, so that's 298 Kelvin units, times the negative 0.4, I'll make that times, 0.4293 kJ per mole Kelvin. Now here's what's happening. Notice the Kelvin units are going to cancel one another and you're left with kJ per mole. So we really will be subtracting like units. And that's the critical point. I mean, if someone is going to make a mistake, one of the most common things we'll do is forget to turn entropy into a kilojoule before we do our subtraction. And that's a critical mistake not to make. So here I have an exothermic value, negative 633.1 minus, and then I'm going to put inside of a parenthesis 298 times negative 0.4293. And I'm going to solve, and my value comes out to be negative 934, and I'm going to round a little bit, 0.5 kilojoule per mole for the Gibbs free energy. So here we found negative 934.5. Originally up here for the entropy, I never did write that there, so let me do that quick. 429.3, and that's a joule per Kelvin mole. Now notice this actually showed a negative Gibbs free energy. See that negative sign? So that reaction comes out to be spontaneous in the forward direction. If delta G came out positive, it would be spontaneous in the reverse direction. Delta G came out negative, so we know it's positive, its forward direction is spontaneous. And if delta G is 0, you're at equilibrium. So both forward and reverse if it's 0. And neither would it not be a choice. What do you think? Take a moment and process the solution pathway. Given thermodynamic values from our standardized appendix, we first used an equation to solve for the entropy of the reaction, products minus reactants. That could be used again for delta H of reaction, and we're about to learn it can be used again for Gibbs free energy, products minus reactants. And that's because all three thermodynamic properties are state values, independent of pathway. Shall we try another? For this reaction, we're given a value of delta H, we're given a value of delta S, and we'd like to know the value of delta G. Why don't you pause the video and work this problem ahead of me? Turn the video back on when you're ready to check your answer. Okay, welcome back. I sure hope you aren't cheating yourself out of the practices. It's very important to independently practice. Pause the video, practice, and come back to me. It's a really good pattern to get into. Okay, so our formula says we want delta G. That's what we're solving for. And I know the relationship says that's found by taking the delta H of the reaction minus T delta S. Now, those values are given to us, so notice I didn't need any appendix values. Delta H is given to me as negative 238.4, and that's in a kilojoule per mole. That's an exothermic reaction. That's favorable. Minus T delta S. Standard state temperature is 298 Kelvin. And look at this, the entropy is unfavorable, isn't it? It's becoming more ordered by that negative sign. Just to remind ourselves, don't fall for this mistake. The 80 joules per Kelvin mole has to go in as a kilojoule, so I'm subtracting like units. And so before you proceed, make sure that you realize that's a kJ per mole requirement. So I divide by 1,000, you move your decimal 3 spots to the left, and you get 0.080 kJ per Kelvin mole. Remind yourself that's an important step. Kelvins will cancel, and now you have kJ per mole, just as you do here, and therefore you're subtracting like units. Critically important to subtract like units. Okay, let me see if I can catch up to you. See if we got a common answer. Negative 238.4 minus, and then in a parenthesis, 298 times, I forgot my negative, times negative 0.08. And my screen reads negative 214.56. I should have just one decimal for sig figs. And that would be in a kilojoule or kilojoule per mole. Yes, this reaction is spontaneous in the direction as written because delta G came out with a negative value. If delta G had come out positive, it's spontaneous in the reverse direction. And if delta G comes out at 0, the system is at equilibrium. So really just a plug and chug formula once we get practicing, isn't it? I made mention just a moment ago that since enthalpy, entropy, and Gibbs free energy are all said to be state functions, which is a way of saying that they are independent of pathways, that allows us to calculate delta G for a reaction just as we did entropy and enthalpy by taking the sum of the Gibbs free energy of products minus reactants. Calculating free energy from standard free energy of formations involves using that thermodynamic table found in our appendix. So again, this is another reaction, another type of state function that allows us to take sum of products minus reactants. And we'll try one of these together. We've done several of these last chapter with enthalpy, and now again in this chapter with entropy and introducing Gibbs free energy. Here we have a reaction, looks like a single replacement reaction. Iron 3 oxide in the solid state is reacting with elemental aluminum. It's foul forming aluminum oxide and releasing the elemental form of iron. And I went into the appendix for us and just did a screen clip and got the thermodynamic values. First column, of course, is always delta H, heat of formation. Second column is the delta G, Gibbs free energy of formation, and the last column is in your delta S. We need to know the Gibbs free energy, so it's focusing on this particular table. Gibbs free energy, I'm going to take a moment and remind us that for any element in its natural state, they're assigned a 0. So notice that the elemental form of aluminum has a Gibbs free energy sign of 0, as well as a heat of formation. And the same is true for iron, assigned as 0, since it's an element in its natural state. So those really just fall out of our subtraction, don't they? The Gibbs free energy for iron 3 oxide is negative 742.2 kJ per mole. And the Gibbs free energy for aluminum oxide is negative 1582.3. So here we have our delta G of reaction is found by taking the sum of the products minus reactants. Well, the product here would be aluminum oxide minus the reactant, which would be iron 3 oxide. And we said the value of negative 1582.3 minus the value of negative 742.2 kJs gives us the overall delta G value. So let's take the aluminum oxide value, negative 1582.3 minus a negative 742.2, and my screen reads negative 840.1 kilojoules. And yes, this is a spontaneous reaction in the forward direction as it's written, because I see a negative sign on the Gibbs free energy. There is a second solution pathway, just to emphasize. You can also find delta G. It's a longer way, but it also works. Delta G can be found by taking delta H minus T delta S. We can solve for delta H by taking the sum of products minus reactants. We can solve for the delta S by taking the sum of the products minus reactants. We would use this column for the delta H. We would use this column for the delta S and plug those into that equation, and I'll tell you what, we'll get the same exact answer as if we had gone to the middle column as we had shown earlier. To emphasize, there are two possible solution pathways. Both will lead you to the same correct answer. Since free energy is a state function, just like delta H, it can be used in a Hess's law application. We can couple reactions to create a spontaneous condition for a reaction that ordinarily would be non-spontaneous, and this is done oftentimes in industry. Here's an example of a reaction. It's the decomposition of a compound called zinc sulfide. So ZnS is a compound, a binary ionic compound, and when it decomposes into its elements, zinc and sulfur come out. Notice this sign on delta G is a positive, so this is a non-spontaneous reaction in the order that it's written, in the forward direction. The decomposition is not spontaneous. The salt, ZnS, will not just all of a sudden decompose and release its elements. It's too stable of an ionic compound. But in the industry, they couple this reaction with a second equation that's quite exogonic, and therefore we can couple this reaction to create a spontaneous condition. Now, what do I mean by coupling? If the original equation was ZnS going to Zn plus S, and it had a delta G of positive 201.3 kJs. The second equation had sulfur combining with molecular oxygen to make sulfur dioxide gas, and its delta G was given as negative 300.1 kJs. Let's add the two reactions together, and that's just called coupling the reactions. everything that's on the left side of the arrow would be ZnS plus S. Well, look at this. Hess's law, do you see it? Notice how this cancels from both sides, and that's fine to do, isn't it? What appears on the right side in the first elementary reaction appears on the left side of the second elementary reaction. So just as in algebra, they're going to simplify out. Therefore, the oxygen is the other reactant, and on the product side, we have zinc and sulfur dioxide. This is missing its 2 over here. And therefore, I can couple those reactions and sum these 2 values together. When I add reactions, I add the delta G's, and when I did so, you can see it come out as negative 98.8 kJs. That now is a spontaneous process. So just like delta H in Hess's law of last chapter, remember those rules? If you flip the direction, you flip the sign. If you distribute a coefficient through a reaction, you'll distribute the same number through the quantity of your delta G, just as practices Hess's law. Here's an example homework problem. Let's read through this together. When an oxide of generic metal, so I'm just going to let the letter M represent any metal from the periodic table, and it's at 25 degrees Celsius. Only a negligible amount of the metal is formed. Notice this is a decomposition reaction. MO2 solid decomposing into the metal and oxygen gas. It has a positive delta G. So right now it is not spontaneous in the forward direction. However, if we couple this reaction with the conversion of graphite to carbon dioxide, it does become spontaneous. So what does that look like? Graphite, we'll write that as solid carbon. It's telling us to do that. Represent graphite as carbon with an S. When it's coupled, it will form carbon dioxide. Well, I'll tell you what, the other ingredient here has to be molecular oxygen, because to make carbon dioxide, you need oxygen. So the conversion of graphite to carbon dioxide, what does that look like for a delta G process? Well, the sum of the products, which would be carbon dioxide, minus the sum of the reactants, which would be solid carbon, plus molecular oxygen, will get us the delta G for that particular process. So let's do that quickly here. And again, I went to the appendix and grabbed these out for us. Delta G's are in the middle column, right? Here's delta H, here's delta G, here's delta S. So notice any element in its natural state is assigned a 0. That's why oxygen is assigned a 0, and that's why we have graphite assigned a 0. That's carbon's elemental form. And so delta G is going to be equal to the carbon dioxide value, negative 394.4, minus 0 plus 0. Elemental carbon and elemental oxygen have no value for delta G. So that delta G up here becomes negative 394.4. We have a positive delta G for the first. That's the decomposition of a metal oxide. That's our first elementary reaction. The second elementary reaction had us couple, right, the conversion of graphite into carbon dioxide, and we determined its delta G by using thermodynamic properties from our chart. So what does the overall equation look like? Well, I noticed that the oxygens are going to cancel one another. And so we have our metallic oxide, which we're using M to represent any metal off the periodic table. When coupled with graphite, and I'm going to write graphite as solid carbon, the element that's the metal will plate out and carbon dioxide gas will form as well. So that's the coupled reaction. When we couple the reaction, what is the delta G of the overall process? Well, this reaction, since we added the two reactions up above, adding equation 1 and equation 2, I'm just going to sum these two values. A positive 289.2 plus a negative 394.4, and I find negative 105.2. And that comes out as a kilojoule for Gibbs free energy. And notice now, based on the sign, it is negative, so therefore it is indeed spontaneous in the forward direction. We coupled a reaction, so we added the delta G's. Adding two equations, we simply add the delta G values. It's an application of Hess's law. Oh, here's a problem from our practice quiz. So this is just an old test question. You may find this on your test. It's in the test bank. We're being asked to calculate the delta G of the following reaction. So this is what I call my target equation. NO as a gas with the atom of oxygen forming NO2 gas. What is the delta G for that reaction? Remember, my strategy says, for no particular reason other than it's written first, I look at the first reactant of the target, NO, and I go into the elementary reactions and I try to find where I locate that. I want to see what side of the arrow it's on. I want to see how many I have. So with NO, I find it in the third elementary reaction. Here's what I like. It's on the left side of the arrow, which is where I want it, and I have just 1 mole's worth, which is what I want. So the first thing I'm going to do is to rewrite the elementary reaction 3 just as it is. Since I didn't change a thing, the delta G remains the same at negative 199.5 kilojoules. Now, for no other reason than it's written next, let's focus on the atom of oxygen. Where do you see it in the elementary reactions? Well, here I'm seeing it in the second elementary reaction. Make an observation with me. What do we like? What do we need to change? Well, in the second elementary reaction, I have 2 moles worth of the atom of oxygen. I only want 1 mole. And I have it on the wrong side of the arrow. So I need to flip the direction, reverse the direction, and I have to distribute a 1/2 through the coefficients. Let's do that and rewrite the equation. So I'm going to reverse the reaction, cutting it in half. So 1 mole of the atom oxygen forming a 1/2 mole of molecular oxygen. I reversed it and cut both coefficients in half. Now, delta G over here was originally 463.4. But I reversed the direction, so I'm going to take the opposite of the sign, and I distributed a 1/2 through those coefficients, so I have to cut that in half as well. So the delta G, when I reverse and distribute a 1/2, now becomes, what's half of 463.2? 463.4. Cut in half is 231.7. And it now becomes negative since we reverse the direction. All right, let's go back to the target equation. And now we're going to focus on NO2. Where do we see the NO2 at? Well, luckily, I see it here. Here's what I like. The NO2 is on the correct side of the arrow. It's on the right side, and I have the correct number for them. So I don't need to do anything there. I'm going to leave that equation alone. What's left to consider is equation 1. Now, equation 1 has got to be used so that when I add these three equations together, I'm going to eliminate some of my remaining targets here. I want to only have left NO, an oxygen, and an NO2. Right now, I still have left, if I think about what's still hanging in here, this ozone is still written here in that elementary reaction I wrote first, and yet it's not appearing in the overall target. And the other thing that's happening is that I've got to get rid of these oxygens. There's no oxygen in the overall target, the molecular form of oxygen, so they have to cancel out as well. So what can I do to cancel out an ozone? I'm going to need it over on this side, O3, so that these will cancel. And I'm going to need 1.5 of the oxygens. And so O2, I'll put 1.5 so that these two will cancel. Now, how do we do that with this? Well, what we've just done is reversed it. So the molecular oxygen was on the left, and we cut it in half. We distributed a 1/2 through all those coefficients. 1.5 is the same as 3/2, isn't it? And if I cut 3 in half, you get 1.5. So here again, we reversed the delta G. It was originally 489.6 positive, but I'm going to reverse the direction, so I take the opposite sign, and we distributed a 1/2 through its coefficient, so I have to cut it in half. And when we do so, we get 489.6 divided by 2, and it becomes negative, so you're at 244.8, and that's also a kilojoule. Now we've eliminated all of those intermediates. The ozones canceled, the 3/2 oxygens canceled, and we've made the target equation from Hess's law. All that's left to do now is to sum those three elementary delta G's to find our target delta G. Let's do that together. Negative 199.5 plus negative 231.7 plus negative 244.8. I get negative 676 kilojoules for Gibbs free energy. Yes, this is a spontaneous reaction in the forward direction. Good fun. That was a review of Hess's law using entropy from last chapter and now using it as Gibbs free energy in this chapter. They are both state functions, which means they're independent of pathway. In this equation, try to make that bigger. There we go. If we consider the decomposition of mercury 2 oxide, here's the mercury 2 oxide. It starts as a compound HGO and it decomposes into its elements. And to keep it balanced, we have a mercury in the liquid form and 1/2 mole of gaseous oxygen. We're being asked first to calculate the free energy change of delta G using standard free energies of formation. Delta G, standard free energies of formation. So the standard delta G is going to be found by taking the sum of the delta G of the products minus the sum of the delta G of reactants. And that would begin by looking at the elemental form of mercury, which we know would be 0. The elemental form of oxygen, which is 0. So the products have no value. They're both assigned zeros. Minus the HGO. And the HGO is, well, I'm in the wrong column. Right here is where I need to look. I went to the second column, but they're still assigned a 0. My bad. The reactant is given negative 58.43, and that's in a kJ per mole. Delta G of this reaction ends up to be 0 minus a negative number, so it comes out to be positive 58.43 kilojoules. This is non-spontaneous in the forward direction, just as we predicted. We can also calculate delta G of this reaction by taking this equation, delta H minus T delta S. And let's actually solve it for this problem so we can compare the two answers, one taking the products minus reactants of Gibbs free energy, and one doing the same for the enthalpy and entropy. Now, we have a little work to do to find delta H of reaction. Notice again, the delta H of reaction, these guys are both assigned a 0. And so the enthalpy becomes 0 minus a negative 90.46, which simply becomes positive 90.46 kilojoules. Delta S of the reaction is found by taking the sum of the products minus reactants, and now they all have values. So we have the product mercury, which is assigned 75.9. And the product of oxygen, it has a coefficient of 1/2. Oxygen's entropy, 205.2. There's the sum of the products. And we need to subtract the sum of the reactant, HGO. Notice why I'm taking 1/2. Our coefficient in front of oxygen was 1/2. So 75.9 plus 0.5 times 205.2 minus 71.13. And I get 107.37. And remember, for entropy, that's joules per Kelvin mole. Delta G of the reaction will be in a kilojoule. Delta H is already in a kilojoule, so that's 90.46 minus, we're at standard conditions, so this is 298 Kelvin, times, I have to put that into a kJ, so it's going to be 0.10737 kilojoules per Kelvin mole. Kelvins cancel, and we're subtracting like units. 90.46 minus, and I'll put this in a parenthesis, 298 times 0.10737, close parenthesis, and we got a value for delta G as 58.46 kilojoules. Came out positive. Look at how close these numbers come out. When we did products minus reactants, we got positive 58.43. Using published thermodynamic values, delta G is H minus T delta S. We got positive 58.46. Very, very, very close. Two solution pathways that lead you to the same correct answer. And again, using thermodynamic properties, this, I believe, is the easier pathway, isn't it? It's fewer subtractions to plug and chug. I'm going to pause the video here. I'm going to come back to finish out this lesson. We've been talking for about 50 minutes already, so it's a good place to stop and pause. Come back to me when you're ready to complete the note pack. We'll wrap it up in the next video.